Welcome back, everybody. How are y'all doing? That good, huh? That good? All right. Well, I've been asked if I could discuss what the heck? If I could discuss number what was this? 17 from the homework? Was it 17? No, 15. So let me talk about number 15. Remember last time what were we doing? Power series, right? 7.6, 7.5, 8.5, whatever. All right. So I'm not going to go through this like in super great detail because there's really only one part of it that I didn't really talk too much about in class. Um, you're trying to find the power series representation of natural log phi minus x using the only that what do we call it, that formula last time, the big, what do we call it, the big time one. And so what we do here is we realize that if we're trying to find the power series for this, then we can look at its derivative, which is this, and that falls into the big time formula. Sorry, I haven't been feeling good. It's going to be hard to talk today. Um, Factor out of 5, make it look like the big time formula right here, and then this turns into this sum. So you're okay up to there, right? And then from here, rewriting it. So I'm taking the 1/5 out of here and putting the 1/5 here and the 1/5 together to get this. Taking the -1 out front. Actually, that -1, that -1 just comes here. The 1/5 goes in here, becomes an n plus 1. And so here's the formula for the derivative of f. That's the power series for the derivative. And then to go back to f, you have to integrate to get back. So we look at the -1/5 to the n plus 1. That's our c sub n. That's the constant, formula for the constant. And then here's our power, our x minus a to the n. And then using the formula I gave you in class to find the antiderivative of both sides, the antiderivative of f prime is f of x. And then over here, what do you do with the constant when you take the antiderivative? Just write it down, right? You don't do anything. And then what's the antiderivative of x to the n? 1 over n plus 1, x to the n plus 1. So that's where this comes from, 1 over n plus 1, x to the n plus 1. But remember, with every time you take an antiderivative, right? When it's an indefinite integral, you have a plus a constant, right? Plus a constant. So what we have is we have an infinite sum, okay, a bunch of powers of x, and each one of those would have a constant. So when you add them all up, you get a constant. So we have some c here. And if you looked at the answer in the back of the book, they actually determined that this c was natural log 5. So how did they determine that this was natural log 5? What they do is they say, what if x is 0? So they just go back and they look at the original function, right? Where's the original function? Right here. Say, what if x is 0? What do you get? You should get natural log of 5, right? But come back down here and look at our power series for f of x, right here. What happens if we let x be 0 here? This is 0, right? So it kills everything off. Everything in this sum is 0, isn't it? And the only thing left is what? Our constant. So f of 0 is that constant. But what was f of 0 from above? Natural log of 5. So that constant must be natural log of 5. Does that make sense? Yeah. Okay. Yes? That kind of clear that up a little bit? Anyone who? Now, picking 0 is just convenient because 0 worked. All right. Pardon me? I'm just going to pick 0 every single time. Yeah, I mean, usually 0 will work because this is a power series and you have x to a power. If that's 0, then it's going to go away. Now what if that was x minus 2? You probably pick 2 to kill the whole series off and be able to get your constant.
Unless x minus equals 0, then.
Pardon me?
If x minus equals 0, then we go with 2.
All right. I have today's notes handed to hand out so that you can follow me. This would have been good a long time ago, huh? All right, so today is our last section. Yep, today is our last section for chapter 8. All right, so hopefully now there's another section, applications of power series, but I don't think I'm going to cover too much of that because really the whole goal is this. Once you've seen Taylor series, once you've seen power series, then when you get to a class like physics or whatever it may be, and they talk about Taylor series, you should be able to adapt what you've learned here into that class. So if you have to integrate something with a series, you'll be able to write the series out and integrate whatever it is. So I'm not going to get into the application so that we can get into chapter 9. All right? So let's talk about today. Lectures, April. All right, let's try and follow this. All right, we're going to talk about Taylor and Maclaurin series. We start by, what the heck is that little thing there? What does this mean? That little symbol right here? It's kind of, it doesn't look right there. This is it's a capital S like this. It means suppose. That's a mathematical symbol we use for the word suppose, all right? Just like we use 3 dots for therefore. Suppose, that's the way we write it, all right? So suppose that there's a function f of x which can be written as a power series. Now this is what we talked about last time, right? A power series is a sum n equals 0 to infinity, c sub n, which is just a constant, right? In front of some powers of x minus a. We did a lot of problems where a was 0, didn't we? And it was just x to the n. And then over here we had this absolute value of x minus a less than capital R. What's capital R? We called that the what? Radius of convergence. Okay, so let's say that we have a function that can be written as a power series. We've seen we can do that, right? Then if we actually expand that series out and actually plug in 0, right? Plug in 0, we get c sub 0, x minus a to the 0. What's x minus a to the 0? 1. So we get c sub 0 times 1. Plug in 1, we get c sub 1, x minus a to the 1, c sub 2, x minus a squared, plus c sub 3, x minus a cubed, right? And that's what this is what the series looks like, all right? We're going to call that equation 1. What we need to do, and this is what Newton was able to do, but Taylor and Maclaurin get their names on it. These are 2 mathematicians because they wrote almost like entire books on this topic. But remember, Newton was the father of calculus. He's the one who really came up with the power series. These guys just kind of really put their stamp on it. All right. So how is it that we can figure out what these constants are? Right? If someone gives us a function, tells us that that this is its power series, how can we determine what those constants are? That's the big question. So we wish to determine what c sub 0, c sub 1, c sub 2, all the way to c sub n are. So what are the coefficients? So the first thing we do is let's let is what I think. It is bad freaking English, man. All right. Let us let x equal a. It still sucks. You understand what I'm saying, though? I like this better. How about this is what mathematicians really like to write. There you go. Why won't that erase? There we go. let x equal a. All right? So if we let x equal a into this first equation right here, what happens? We get f of a equals c sub 0 plus c sub 1. A minus a is 0. Over here, c sub 2, a minus a is 0. So do you see that what we'll get is f of a equals c sub 0 and then a bunch of zeros? So doesn't that mean that f of a equals c sub 0? So our first constant is this function evaluated at a. Okay? That's the first constant. Now what we're going to do is take the first equation, which is right up here, and we're going to differentiate both sides. So what's the derivative of f? The derivative of f prime. What's the derivative of a constant? 0, derivative. Yeah, you did anti. So derivative of a constant is 0, so it's gone, right? What's the derivative of c sub 1 x minus a? Well, c sub 1 is a constant, right? What's the derivative of x minus a? With respect to x? 1. So derivative of x minus a is 1 times c sub 1, which gives us, where the hell is it? C sub 1, right? I did power rule here. I brought the 1 down and subtracted. You don't really need that. What about this next one? What's the derivative of this? Power rule, right? 2 comes out. 2c sub 2. X minus a to what power? First power, right? Now do the next one. What's the derivative of c sub 3 x minus a cubed? 3 comes out. 3c sub 3 x minus a squared. Do y'all see what's happening here? Next one would be 4c sub 4 x minus a cubed. Follow? Yes. Yeah, but what's the derivative of x minus a? 1. Yeah, so for each of those it's 1, isn't it? Because a is a number, but c is our variable. That's good. At least you were wondering where the chain rule was. It was there, though. Okay? Now, this is our derivative right here. That's the derivative. All we did was just took derivative of both sides. That's equation 2 now. What I'd like for us to do is, again, let x equal a. If I let x equal a, what happens? Everything that has x minus a in it goes to zeros, doesn't it? Gone, gone, gone. And all you get is c sub 1. So the first derivative evaluated at a, that means plugging a in here, turns out to be just the c sub 1. Are you, yes? So c sub 1 is f prime of a. And we continue. Now we take the derivative again. So I'm taking this one in this box, equation 2. I'm taking the derivative again, which would be the second derivative. So I use this little notation, right? This means second derivative. Second derivative of the function at x is equal to, well, derivative of c sub 1 is nothing. Now what happens here? What's the derivative of 2c sub 2 times x minus a? 2c sub 2. Drop the power, which makes it a 0 now. And anything to the 0 would be 1, right? What's the next one going to be right here? 6, which I'm going to write as 2 times 3. Now, I understand 2 times 3 is 6, but just follow this. 2 times 3, c sub 3, x minus a to the first power. Then this next one becomes what? 3 times 4, c sub 4, x minus a squared. And that keeps going, that pattern. Again, plug in a. What's the second derivative with a plugged in? Everything gets killed off except 2c sub 2. Sorry, I forgot to turn my phone off. All right. So there's the formula. The second derivative of the function evaluated at a is 2c sub 2. Dividing both sides by 2, I get c sub 2 equals the second derivative of f at a divided by 2. And we go again. So now I'm taking derivative of equation 3. What's derivative of 2c sub 2? 0. What's derivative of 2 times 3 times c sub 3? X minus a times x minus a. Just 2 times 3 c sub 3. And then the next one, watch what happens. 3 times 4 c sub 4, all this squared. 2 comes out. 2 times 3 times 4 c sub 4 x minus a. And then I keep that pattern going, right? When I plug a into the third derivative, I get 2 times 3 times c sub 3. Divide both sides by 2 times 3 here, and you get that the third derivative at a times 2 times 3. What do you think the next one is going to be? Without even doing all this work, what do you think the next one's going to be? What's c sub 4? The fourth derivative of fourth derivative of f at a divided by 2 times 3 times 4. The fifth one would be fifth derivative of f at a over 2 times 3 times 4 times 5, right? It's a factorial. So what we're getting is, see, I did the fourth one. 2 times 3 times 4 is the same as 4 times 3 times 2 times 1, which is 4 factorial. So when we go to the next one, f fifth derivative, right, it would be 5 factorial. So the nth term, the nth constant, is the nth derivative of the function at a over n factorial. That's the big time result, the second big time result. And that allows us to create this theorem, which is known as the Taylor series. So here's what it says. And this is called a Taylor series of a function f at a. You might also hear it said a Taylor series of a function centered at a, or Taylor series of a function f about a. Do you have a question? It's not in there? Did it? Okay. I wonder how much else is missing. That's weird. Oops. Well, write it down. It's going to be the one in this box. Actually, there's two. But let's talk about it. Before you write it down, let's just talk. What this says is this. If you've got a function, right, that can be written as a power series, if that's true, that you can write the function as a power series, then these coefficients, the c sub n's, is this, right? That's what we just came up with. And therefore, we can rewrite that series replacing the c sub n with this right here. And that is basically like Taylor's formula right there. That's what you should write down. And I'll put it on the board over here also. And this is one of those ones that you should just probably have memorized, right? N equals 0 to infinity, nth derivative at a, man, this marker sucks, over, that one's even worse, nth derivative at a over n factorial, x minus a to the n. Sorry that looks so terrible. Okay, that is the Taylor series of a function about a, or centered at a, or at a. Also make note that, remember, it starts at 0, right? Starts at 0. So what's f0? That means the 0th derivative, which means don't take a derivative. That means the function. So that's what I put over here. The 0th derivative at a means f of a. Also, 0 factorial by definition is 1. That's one of the strangest things that I remember seeing as a student, is that 0 factorial is equal to 1. All right? And I'm not here to have a discussion about this, but it's a very sound mathematical thing that this is 1. If you're interested in it, just go Google factorial, and it'll talk about this important property right here, but it's really beyond the scope of this class. It's a more advanced math topic, all right? Hmm?
What are you trying to say?
Well, it's very difficult to it's difficult to explain because you have to understand what factorial means to begin with. Like factorial means that you're taking the product of a number times a number, keep reducing by 1. To say 0 factorial means it doesn't mean 0 times, it doesn't mean like 0 and keep going down. Right? 4 factorial means 4, 3, 2, 1, done. 1 factorial means 1 and you're done. 0 factorial doesn't mean 0. It means you have nothing to multiply. And when you have nothing to multiply, the factorial function returns the multiplicative identity, which is 1. So it's just a property of those types of operations, and again, it's beyond the scope of the class. But just know that this is well defined and it widely accepted. All right? I mean, that's the way it is. All right, that allows us, when we plug in 0, that's 1 and we don't get division by 0. All right, now, what if A is 1? I mean, sorry, what if A is 0, right? Here's Taylor's formula. What if A is 0? That means we have x to the n out here, right? Then we'd be plugging 0 in here also. So what we get is this formula. So if you do a Taylor series centered at 0, not at A, centered at 0, this is the formula, right? Y'all see the difference? And this series is called the Maclaurin series. So a Maclaurin series is a very special case of a Taylor series. It's a Taylor series with A being what? 0. Okay? How many of you have ever watched Good Will Hunting? Yeah? Do you remember the scene in Good Will Hunting when Matt Damon's character goes into the professor's office and the professor's sitting there reading one of his papers? It's the scene where like he starts burning the paper and the professor's like, no, remember that? No? Anyway, when the professor's reading his work, he sits there and in one of the quotes he says, oh, I see you use Maclaurin here. He's talking about this in the movie. He's talking about Maclaurin series. That, of course, when I watch a movie like that, I'm always looking to make sure like the math looks like it's, something. Of course, I couldn't understand the math that he did on the board in the beginning of the problem. I mean, at the beginning of the movie, but. So, Maclaurin, Taylor. Maclaurin is a special case of Taylor. That's all it is. All right, so we're going to do our first example. We are going to find the Maclaurin series for sine of x. Now, the work is all here for you. So do you want me to work it out, or do you want me to just talk through it? How many of you want me to talk through it? All right. I guess the rest of you want me to work it out. Yes? I'll work out this first one. Let's see how it goes. So find Maclaurin series for f of x equals, I'm going to change it up, okay? Because I have sine x worked out in here, right, already. I already have sine worked out, so I'm going to do something else. I think it's just a little too easy for me to do sine. So I'm going to do cosine x. All right? Now, according to what today is about, I'm trying to write out a series, a power series that represents this function, right? An infinite series, power series. And in the previous class, in order for me to do it, I had to make it look like that big time formula, didn't I? The beauty of the Taylor series is that, and the Maclaurin, is that you can now generate the series yourself just by knowing derivatives. That's what will allow you to do this, Okay? So what we normally start with is taking derivatives. So what's the first derivative of this function? Negative sine x, right? What's the second derivative? So what's the derivative? I forgot to put negative, didn't I? Negative sine x. What's the second derivative? Negative cosine x. What's the third derivative? Positive sine x. What's the fourth derivative? So now I'm going to start using the little 4. You have to put that 4 in parentheses, right? If you don't, what does it mean?
It's the four.
Fourth power, and that's not what you want, your fourth derivative. So what's the fourth derivative? Cosine x. And now it starts to just repeat itself, doesn't it? It'll go now again to negative sine, then negative cosine, then sine. All right. So I'm going to say dot, dot, dot. Now next to this, and I'll do it in red, I want to know, remember what we're supposed to do for Maclaurin, and I didn't write Maclaurin on the board. I think I'll put Maclaurin on the board over here. Maclaurin is this formula replacing all your what's with what? All your a's with zeros. So Maclaurin looks like nth derivative at 0 over n factorial x to the n instead of x minus a because that's 0. So this is what I'm trying to do, right? So I need all the nth derivatives, and I need to plug what number into each one of them? 0. So what I'm going to do next to this is I'm going to do the first derivative at 0. What's the first derivative at 0? So what's sine of 0, everyone? 1. Oh, I think I'm like calling people in my pocket. Oops. What's going on with this phone? Sine of 0, everyone. Sine of 0, 0. Okay, what's the second derivative at 0? What's cosine of 0? Cosine of 0 is 1, but then it's negative in front. So negative 1. Okay, what's the third derivative at 0? What's sine of 0? 0 again. Okay, what's the fourth derivative at 0? 1. And now we said this was going to continue the pattern, right? So the next one's going to be 0, then negative 1, then 0, then 1, then 0, then negative 1, then 0. Okay. Any questions? So here's the Maclaurin. I'm going to write out our Maclaurin. So my Maclaurin is the sum n equals 0 to infinity, nth derivative of f at 0 over n factorial x to the n. So let's start with n is 0, right? We get the 0th derivative at 0 over 0 factorial x to the 0. All I'm doing is replacing all my n's with 0 first. Plus, now the first derivative of the function at 0 all over 1 factorial x to the 1 plus the second derivative of f at 0 over 2 factorial x to the second, right? Y'all follow what I'm doing here or not? I know what all these are because I just got these up above. I'm going to bring them back here in just a second. Except I didn't get this one. Did I? I didn't do that one, did I? No. Okay, good. We'll deal with that in a second. Okay, so what's my next term? F, right? Third derivative at 0 over 3 factorial x to the third. Plus, I'll do one more. Fourth derivative of f at 0 over 4 factorial x to the fourth. Plus dot, 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 dot forever. Now let's plug some stuff in. What is the zeroth derivative of f at 0? What does that really mean? Zeroth derivative means just f, right? That just wants f of 0, doesn't it? What's f of 0? Well, what was your function to start this problem? Cosine x, right? So isn't this cosine of 0? What's cosine of 0? 1. Right? So what we get here is 1 over, what's 0 factorial? 1. What's x to the 0? 1. Okay, plus, what was the first derivative of the function at 0? So go back up to our table. What's the first derivative of the function at 0? What was the first derivative at 0? 0, right? So this is going to be 0 over 1 factorial x to the first plus, now, what was the second derivative at 0? Negative 1, right? So we had negative 1 over 2 factorial x squared plus, what was the third derivative of the function at 0? 0 over 3 factorial x to the third plus, what was the fourth derivative? What was it? 1? 1 over 4 factorial x to the fourth plus dot 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 forever. Any questions? Now, the zeros in some of these are going to kill them off completely, aren't they? So like this 0, this one's gone, this one's gone. So what I'm left with is this. 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the fourth, right? That's the first term, second term, those three right there, right? Anyone guess what the next one would be? Minus, it'd be minus 1 over 6 factorial x to the sixth. What do you think next one would be? Plus 1 over 8 factorial x to the eighth plus dot dot dot. That's the power series representation of cosine x using the Maclaurin series expansion. So basically using it, the Taylor series at 0. Now remember the other class I had y'all do like e to the x? The very first thing I did in class, I said, everyone get your calculator out, let's do e to the second power. You did it on your calculator, and then we did that series and we plugged in 2 and it got real close. The same exact thing. If I want to know what cosine of something was here, I could plug it in here. By the way, what's cosine of 0? 1. What would happen if you plug 0 in here for x? 1. Okay? I mean, this should spit out whatever cosine of that value is. With me? Now, we're not done. We have a little more to do. But how many of you remember a property in pre-cal that the cosine function was even? Remember what even meant? What is the property of an even function? F of negative x equals f of x. That's what it meant for a function to be even. It meant that if you plug negative into it, it's the same as not plugging negative into it. It also meant that if you graphed the function, that it was a reflection of itself over the y-axis. That plugging in x was the same as plugging in negative x. Well, guess what? Look at this. What are all the powers on x's here? They're all even. And that means if I plug an x in here, it's the same as plugging a negative x in, because when I square it's the same as positive. And guess what? The sine function was odd, wasn't it? So guess what the odd power series looks like? It's a bunch of odd powers of x's instead of even. All right, that's just another topic. But all right, so now our final goal here is for us to write this as a sigma notation and then find the radius of convergence. Those are the last things we're going to do. So how could I write this as in sigma notation? What do you notice about this series? It's alternating, isn't it? Positive, negative, positive, negative. How do I make a series alternate? Negative 1 to the... Now, I'm going to start at 0, right? N equals 0. That's where I'm going to start from. So how do I make my first term positive by using what power on the negative 1? You could do n plus 2. You could also do just n. Because if I start at 0, what's negative 1 to the 0? 1. And then when I plug in 1, I get negative 1 to the 1, which would be negative. Plug in 2, I get 0 again. You see what? I mean, 1 again. So does everyone see this negative 1 to the n? First of all, will start us alternating, starting at positive. Okay, someone tell me about the powers of x. X squared. X to the fourth, 6, 8. They're all even numbers. How do we get even numbers? 2n, right? But we need our first power on x to be what? Right here? 1x to the what? 0, right? That's x to the 0 here? So 2 times 0 is 0. So we should be able to put in here for the power what? X to the 2n. All over. Tell me about the factorials. What about the factorials? They're the same as the powers, aren't they? 6, 8. So 2n factorial in parentheses. And what would I get if I plug 0 in here for n?
1, 2.
I get 2 times 0, which is 0. What's 0 factorial? 1, and that would take care of my first one, wouldn't it? This is the mathematician's formula for cosine x. That's the power series, the Maclaurin series for cosine x. Your calculator does this right here, and it just at some point stops at some preset tolerance within the calculator. All right, you ready? You ready to find the radius of convergence? How do you find the radius of convergence? Ratio test. So I'm going to do ratio test on this. Limit n goes to infinity. All right. Do I need to consider the negative 1? No. Plug in right here n plus 1. This becomes x to the 2n plus 2, right? When I plug in n plus 1 right there, the 2 distributes to the n and to the 1. Right? Because the n is replaced with n plus 1, then the 2 goes to both. And then on the bottom, same thing, right? Over 2n plus 2 factorial. And then times 2n factorial over x to the 2n. Anybody have a question on how I set that up? How can I rewrite this top left so I can get cancellation down here? Separate it. What would it be separated? X to the 2n, x squared, over. Now, on the factorial on the bottom, I need to start peeling them off, right? Peel 2. So 2n plus 2. Then what? 2n plus 1. Then what? 2n factorial. Times 2n factorial over x to the 2n. I'm hoping, like, by doing the homework, if you did the homework, this should be almost kind of routine at this point. You've done it. If you did the homework like I did enough of this shit that this is okay now for me, okay? I mean, it's a lot. The last homework assignment was a lot. So, let's see. Cancellation, x to 2n, 2n factorial, 2n factorial. And now I'm ready to let this go to infinity in a second. My next line Let's see, what's still here? I got x squared. I'm throwing it at the end. I still have the 2n plus 2 on the bottom, the 2n plus 1 on the bottom, and then next to it, absolute value of x squared. So the reason I don't put the 2n plus 2 and 2n plus 1 in the absolute values because they're positive, right? N's positive, so this is all positive. What does that go to as n goes to infinity now? 0, right? This first thing here is a constant, a fixed number over infinity. That goes to 0. This limit goes to 0, right? And what was it that we were looking for? For convergence, we needed this limit to be what? Less than 1, right? This was equal to our L, and that's less than 1, and that guarantees convergence, doesn't it? That means it converges no matter what x is, right? It always converges. So what does that mean our radius of convergence is? Therefore, our radius of convergence is infinity. That's basically saying that your x value can be anything you want, right? And this thing will converge. No matter what x is, you give me an x, give me a number, I don't care what it is. Boom, I put it right there, and I let n go to infinity, this sucker's going to 0. And therefore, no matter what x I pick, that series will converge. Therefore, the radius of convergence is the length of this interval, and that interval is infinitely long, so the radius of convergence is infinity. Make sense? Okay. Now, let's look at the example. Let me see. I'm going to write down real quick here what we just got. We said cosine x equals 1 plus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th plus 1 over 6 factorial x to the 6th plus dot, dot, dot forever, right? Yes? And in your notes, I was going to do this one, but I said, no, I'm not going to do this one because it's sitting here in your notes, right? Did I do it on here? Is it in here? What was the Maclaurin series for sine x according to my notes? Don't give me the sigma notation. Give me the one right above it. What was it? X. Oh, wait, hold on. I forgot to alternate my damn series up above. It should have been 1 minus and then plus and then minus, right? Do y'all see that? I just wrote that down. I forgot to alternate my series. So 1 minus and then plus and then minus, right? Yes? Okay, what was the one I got from sine according to my work here? X minus 1 over 3 factorial x to the 3rd plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th plus dot, 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 dot. Okay? Yes? What's the derivative of sine of x? What's the derivative of sine of x? Cosine x. I want you to take this series right here for sine, and I want you to take its derivative right now. What would you get? If I take just this line right here and I take the derivative, what's the derivative of x? 1. Minus, okay, what about this one? What's the power rule say? 3 comes out in front, right? So I would have a 3 over 3 factorial, but what's 3 factorial? 3 times 2 times 1, x squared, right? Plus 5 would come out, 5 times 4 times 3 times 2 times 1, x to the 4th, minus 7 over 7 times 6 times 5 times 4 times 3 times 2 times 1, x to the 6th, right? And what cancels? 3's cancel, 5's cancel, 7's cancel. And isn't this 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th? And isn't that cosine x? Isn't that beautiful? And it works the other way around. Check this out. What's the derivative of cosine x? Negative sine x. So what would be the derivative of 1? 0. What's the derivative of this right here? 2 would come out, 2's would cancel, and you just get negative x, wouldn't you? So that's x, but the derivative of cosine is negative sine x, so instead of being x, it's negative x. And you could do that and show that it's the same, just off by a sign. Pretty exciting stuff, huh? All right, so let's see what our next problem is here. Okay, I have this in the notes. I'm just gonna show it to you, but I'm not gonna write anything on the board. Where are we? Maclaurin. Oh, whoa. There it is. The book talks about the nth degree Taylor polynomial of f at a. And I don't want to get into it because I'm not going to test you on it. I don't think it's critical for this class. You might recall when we were talking about series a long time ago, before we even got into power series, when we were talking about like just numbers added up, that there was some formula for the error that you would get. And I said, I'm not going to cover it. This is the same sort of thing. I'm not going to cover it. The nth degree Taylor polynomial means instead of taking an infinite sum, you stop it at some point. If you stop it, then it becomes a finite series. And therefore, the original function, if it's an infinite series, can be written as a finite series plus some remainder. The remainder would be the rest of the series if you went to infinity. That remainder has this as a formula for the remainder. And we can actually look at this formula for the remainder and check to see that it goes to 0, to confirm that the function can be written as a Taylor series. I'm not going to do that in this class. We're just going to assume that the functions can be written, that the Taylor series exists. But I just want you to know that that was in the book. It talks about it a little bit. Even in the problems I assigned for you for homework, it'll mention this, and it'll say you do not have to show that r sub n of x goes to 0. So you'll just skip that part anyway. All right, we need to find the Maclaurin series for these now. So let's do e to the x. Now I gave you the power series for e to the x at the beginning of last class, right? If you go to last class, which was a long time ago, when was it? Here? Here it was. Right? Remember that? That was the first thing I did in class last time. I said, hey, get e squared on your calculator. And I said, okay, if I told you that e to the x was this, check on your calculator that this gets close to that, right? Where does this come from? We actually have a way of figuring it out now ourselves. We can come up with the power series for functions now using Taylor's formula. And that's what we're going to do. All right, so what do we need to start with? Derivatives, right? Now, depending on how you want to do this, you might want to get used to first doing the zeroth derivative, because you're going to need that in the formula, right? The zeroth derivative. What's the zeroth derivative of e to the x? It's just e to the x, right? What's the first derivative of e to the x? E to the x, right? Itself. What's the second derivative of e to the x? I'm changing my notation up here, sorry. E to the x again, this is boring. What's the third derivative? You're stuck? Too late to drop the class, sorry. E to the x again. So this just keeps going, right? Now I want to do, since this is a Maclaurin series, I want the zeroth derivative evaluated where? Since it's a Maclaurin series? At 0. A is 0 for Maclaurin. First derivative evaluated at 0. Second derivative evaluated at 0, and so on and so forth. But all of these are the same function, aren't they? E to the x, e to the x, e to the x. What's e to the 0? 1. 1, 1, 1, 1, 1, 1, right? So 1, 1, 1, 1. That's pretty boring. Questions? Here comes Maclaurin. Maclaurin says that I should have sum n equals 0 to infinity. The nth derivative evaluated at 0 over n factorial x to the n, which is I don't know how much detail y'all want here. Do you want me to write out 0th derivative at 0 over 0 factorial plus first derivative at 0? I'll do it, I think for this one I'll do it one more time, but from here on out I'll probably just jump right to what it is. 0th derivative at 0 over 0 factorial plus first derivative at 0. Oh, I forgot something in there. What did I forget? X to the 0 plus first derivative of f at 0 over 1 factorial x plus second derivative at 0 over 2 factorial x squared plus third derivative at 0, 3 factorial x to the third plus dot 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 forever. But what do you get when you plug 0 into the 0th derivative? 1. And 0 factorial is 1, and x to the 0 is 1. So you get 1 plus, what's the first derivative of f at 0? 1 again over 1 factorial, which is 1 times x, so just x, plus every one of these derivatives we just set up of our table was 1, wasn't it? So now we get 1 over 2 factorial, which is 2, x squared, plus 1 over 3 factorial x cubed, plus dot 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 dot, forever and ever, amen. And can you write that using sigma notation? You can kind of see it from right here. Look at the bottom. What is the denominator always going to be? Factorial, right? It's just 0 factorial, 1 factorial, 2 factorial, 3 factorial. So that's just n, isn't it? So the bottom is n factorial. The top is just x to these powers, right? X to the n. And there's no alternating in this series, so we don't have to worry about a negative 1. So that's the Maclaurin series for e to the x. I probably already showed you this. I think I remember doing it. What's the derivative of e to the x? E to the x. So look at this right here. Take the derivative of that. What would you get? What's the derivative of 1? 0. What's the derivative of x? 1. What's the derivative of 1/2 x squared? So 2 comes out, you get plus x. This one right here, the 3 comes out, cancels with the 3. You get 1 over 2 factorial x squared. 1 over 2 factorial x squared. And then the next one would be 1 over 3 factorial x to the third. And guess what? That is itself. So e to the x is its own derivative, right? There's only one other function that's like that, and it's the constant 0 function. Right? Think about f of x equals 0. What's the derivative of f of x? 0. So the only other function other than e to the x that is its own derivative is the constant 0 function, which is what we call a trivial function. It's boring. It's not doing anything. E to the x is the only function, okay, that is its own derivative, and that when you plug in 0, you get 1. That's what makes e to the x e to the x. It is the only function that exists where it is its own derivative, and f of 0 is 1. You'll never be able to find another function out there, none of them exist, where the derivative is always itself and the function evaluated at 0 is 1. All right, now we've done Maclaurin. We've done 2 Maclaurins, right? We haven't done a Taylor series yet. So let's do a Taylor series. So the next one I'd like to do is find Taylor series about a equals 2 of f of x equals e to the x. So the main difference in this problem is that it's a Taylor series now. So a is not 0, a is whatever they give you. And in this problem I have to give you what it is, and it's 2. So we're going to use that top formula over there on the side instead of the Maclaurin. But the same thing still exists. We still need to take derivatives, okay? So let's start out with our little table here. The 0th derivative of the function is itself. The first derivative of the function is itself. The second derivative of the function is itself. Boring. However, oh, by the way, on that previous problem, I didn't do ratio test. That would be something you'd have to do in your homework. I'm done with ratio tests for now. You're done also? Good job. Good job. All right. Here we go. What's the 0th derivative at where? At 2. Not at a. I mean, not at 0, at 2, because a is 2. So that means take your 0th derivative, which is e to the x, and plug in 2, and you get what? E squared. All right. What's the first derivative at 2? E squared again. What's the second derivative at 2? E squared again. Boring, but yeah, that's what's happening. All we're doing is taking the derivative, whatever it was, and we're evaluating it at 2. And for this particular problem, the derivative was well behaved. It just stayed itself the whole time. So now I'm ready to go with my Taylor series, right? So for Taylor, I have sum n equals 0 to infinity, nth derivative at a, right? Which is actually 2, isn't it? Over n factorial. What here, though? X minus 2 to the n. So let's start writing these out. What's the 0th derivative at 2? E squared. Over 0 factorial, x minus 2 to the 0. Plus, now I'm going first derivative. So this time I'm not writing them out. I'm not writing the f0, f1, f2. I'm not writing. I'm actually just putting them in. So what would the next one be? E squared over 1 factorial, x minus 2 to the first power, which I don't need, plus e squared, 2 factorial, x minus 2 squared plus, that's good enough. What is that first term? Just a 1, right? It's just a 1. Can we come up with sigma notation for this? N equals 0 to infinity. What are all the denominators? Factorial, just n factorial again. What about the numerators? How about, they're all e squareds, aren't they? So e squared. And then not x to the n, x minus 2 to the n. So you can put it out here at the side or on the top, wherever you want. That is the Taylor series of e to the x centered at 2. Yeah. Yeah, because this first one right here, that's the zeroth derivative at 2. That's e squared. That okay? All right. What's still on here? I'm not ready to do the next one. I'm kind of working off this sheet where I have examples written down here. You see that? I don't think I'm ready to do the Maclaurin series for 1 plus x to the k. That's going to be not good. All right, fine. Taylor series. You would still need the radius of convergence for that problem, okay? I'm not going to do it, but that's what you need. Find Taylor series for... You don't? What? For... I'll do that one next. F of x equals natural log x at a equals 3. All right, here we go. What is the zeroth derivative of f? Itself, okay. What is the first derivative of natural log of x? 1 over x, which is the same as x to the negative 1, isn't it? Okay, what's the second derivative of f? Negative x to the negative 2, which is negative 1 over x squared, right? Everyone with me on that? What's the third derivative? You tell me, yeah. 2x to the negative 3, which is 2 over x cubed. Yes? Fourth derivative is what? Negative 6. Now watch what I'm going to do. I'm doing this on purpose. It's actually going to be negative 2 times 3 over, well, let me do it this way. Negative 2 times 3 x to the negative 4, which is negative 2 times 3 over x to the 4th. I want to go a couple more because I want you to see the pattern. See, these are a little more complicated, right, than just, what, e to the x, e to the x, e to the x. That was kind of boring. Okay, fifth derivative is what? Negative 2 times 3 times, oh, wait, not negative, positive, right? Because I have a negative out here. The negative comes out, hits a negative, becomes positive. So 2 times 3 times 4x to the negative 5. So this is 2 times 3 times 4 over x to the 5th. Next one. I'm going to go out as far as it takes for you to see the pattern.
I see the pattern.
You see the pattern? What's the next one?
Negative 2.
Negative 2 times 3 times 4 times 5 x to negative 6, which is
2 times 3 times 4
yep,
times 5
negative
over
2
negative
times
6.
3 times 4 times 5 all over x to the 6th. So what are we getting in the numerator?
Factorial.
We're getting a factorial, but see, like if I wanted to do like the nth derivative,
How will you?
then what would you get? Well, it's alternating signs, isn't it?
Yeah, so it's negative 3.
So when is it negative? It's negatives on the evens, isn't it? It's negatives on the evens,
Oh, I didn't do it like that.
isn't it?
Yes.
So I would need to go like negative 1 to the, if I plug in 1 for n, I should get a positive, right? If I plug in 2 for n, look, the second one should give me a negative, right? If I do the second derivative, I should get a negative. If I do third derivative, I should get a positive. Fourth derivative, a negative.
N minus 1. N plus 1 or
You could go n plus 1 or minus 1, right? Let's check this. If I plug in 6 right here, sixth derivative, what's 6 plus 1? 7. Negative 1 to the 7th is negative. So that's going to give me a negative, right? If I go to the fifth derivative, what's negative 1 to the 5 plus 1 is 6. Negative 1 to the 6 is positive, right? This should take care of the alternating, shouldn't it? What about the numerator? 2 times 3 times 4 times 5. It is factorial, but look, this was 6 here, wasn't it? That's not 6 factorial. That's 5 factorial. This is 5 factorial. That's actually 4 factorial. This is 4 factorial. So it's n minus 1 factorial over x to the n. Do y'all see that? Question? Okay. All right, now let's go make a table next to this here. What's what's f sub 0 at, where are we evaluating? At 3. That's natural log 3, isn't it? What's the first derivative evaluated at 3? 1/3. What's the second derivative evaluated at 3? Negative 1 over 3 squared. I agree that's a 9. That looks like a 32. 3 squared, right?
Oh, it's 3 cubed, 3/4.
What's the third derivative evaluated at 3? 2 over 3 cubed. Yes, positive. I don't know why I did that. So I'm going here to here, right? What's the next one? Fourth derivative at 3 would be negative 2 times 3 over 3 to the fourth. Yes, I agree. You could cancel 3, but we're trying to get a pattern here. Fifth derivative at 3 would be positive this time. 2 times 3 times 4, 3 to the fifth. We'll do one more. Sixth derivative at 3 would be negative 2 times 3 times 4 times 5 all over 3 to the sixth. Okay, I want you to take a minute. My phone is about to die. I've got to make a quick phone call. Uh-oh, it's too late. It's already dead. Never mind.
Somebody else has to. It was just my wife. Kids can just stay at daycare.
Yeah. So those are all your numbers. Now, are you ready to write out the Taylor series? so here comes Taylor. Taylor's going to be sum n equals 0 to infinity f the nth derivative at 3 over n factorial, not x to the n, x minus 3 to the n. Okay, which equals? What was the first constant we got? So I'm trying to plug in n equals 0, right? That gives me the 0th derivative at 3. What was the 0th derivative at 3? It was natural log of 3. It'll be divided by 0 factorial, which is 1, and then x minus 3 to the 0, which is 1. So my first term is natural log 3 plus. What was the first derivative evaluated at 3? 1/3 over n factorial, which is 1 factorial. I'm going to write it down. X minus 3 to the first power. Plus, what was the second derivative evaluated at 3? It was negative, what? 1 over 3 squared. Over 2 factorial, x minus 3 squared. Are y'all following this? All these numbers right here, the natural log 3, the 1/3, the negative 1 over 3 squared, those are all my little c sub n's that I got from, taking the derivatives and plugging in. The n factorial, x minus 3 to the n, that's just part of Taylor's formula. That's just this part right here. What's the next one? Plus 2 times 3 over 3 cubed over 3 factorial x minus 3 to the third. What is it? What? Oh, yeah, it was 2 over 3, not. Thank you. I'm out. I'm done. Let's go one more. This one would be what? Negative 2 times 3 over 3 to the fourth over 4 factorial x minus 3 to the fourth. One more. 2 times 3 times 4 over 3 to the fifth over 5 factorial x minus 3 to the fifth. What would the next one be? I'm not going to write it down. What would it be? Negative 2 times 3 times 4 times 5 all over 3 to the sixth over 6 factorial all times x minus 3 to the sixth. All right. Now, this is where it gets a little challenging on this problem. I want the sigma notation. All right, I want the sigma notation. Because we want to get a ratio test, and you need it in sigma notation to get a ratio test. So let's start looking at this. What was happening? I mean, what's the most easiest? Yes, what was the most easiest thing to see down here? N factorial? And maybe it's worth it for you to look at this first one and write it like this natural log 3. I'm going to write natural log 3 over 0 factorial x minus 3 to the 0. Right? That was that first one. So does everyone agree all the denominators, the factorials, it's like if we started 0 with n, it would be n factorial for the bottom. All right? Good. Happy with that. What else? X minus 3 to the n also, right? X minus 3 to the n, x minus 3 to the n. Those keep going up. What's wrong though? What's the problem here? There's an issue we have to deal with. Tell me about these fractions here. Just cover this up for a second. 1/3, right? It's alternating, but not here though, right? It's positive, positive, positive. Wait, no, hold on. Where's my negative? It's positive, positive, negative, positive, negative, positive. So it doesn't start alternating right away, does it? Yeah. Okay, so the numerator of this fraction is a factorial, isn't it? It's 1, and then, but wait a minute, it's 1 again? And then it's 2, and then it's 2 times 3, then it's 2 times 3 times 4, then it's 2 times 3 times 5. There's some weird stuff happening here. Do y'all see that? It's not as clear as the last problems we've done.
0 factorial is 1.
Okay, 0 factorial is 1. 1 factorial is 1. And then 2 factorial, 3 factorial, 4. Okay, I'm with you on that. But if this is 0 factorial, that's 1 factorial, then if we're calling this n, then we can't call that n. We have to call it what? N minus 1. It's starting to get crazy. All right. And then what about the 3's on the bottom here? 3 to the first, 3 squared, 3 cubed. So the power keeps going up. So it's like 3 to the n. What we got to do, I mean, you look at this and you try and start to see where pieces are, and then you just got to write a formula down and see if you can make it work. Okay? So here's the way I'm going to write this down. First of all, the first term here, natural log of 3, doesn't follow my pattern because the natural log of 3 is not one of these fractions, is it? Like every one of these, it's 3, then 3 squared, then 3 cubed, then 3 to the 4th, 3 to the 5th, 3 to the 6th, right? Natural log of 3 is not 3 to a power. So the way I'm going to write this is as follows. Equals natural log 3, that's the first term, plus, now I'm going to start my series, okay? So I'm saying, look, I concede, all right? I give up. Natural log of 3 cannot be part of my formula for my sum, all right? Can't be. Now, from here on out, I've got a formula. Now, where should we start it? Where do you want to start it? We got to try with something. Okay, you want to try n equals 1? To infinity. All right, let's try and make this happen. Let's take care of the alternating first. We want the first guy to be positive, the next one to be negative, then positive, then negative. So how do we start with the positive? Negative 1 to the, where are we starting at? 1. So n, what is it? Plus 1, or you could do minus 1. So if I start at n equals 1, because that's what I was being told to do here, if I start at n equals 1, then if I plug in negative 1 to the n plus 1, if I plug in 1, I get negative 1 squared, which would give me a positive term, and that would be this first one. I'm working from here this way, right? This guy I don't even care about because I wrote him down in the beginning here, natural log 3. So that should start me out with the positive. Then it's going to go negative, positive, negative, positive. So that takes care of the alternating. Okay, then next part. To me, the easiest thing that I see right now is the bottom is n factorial. Because that's 1 factorial. That would be 1 factorial. Then it would be what? 2 factorial, then 3 factorial. So I'm going to put over here 1 over n factorial. Everyone agree with that? What's the next easiest thing that you see? The x minus 3 is to the n power. What's the next thing that we need to deal with? The fraction, this thing right here that was causing all the issues. What did we say the numerator was? It was n factorial, but look, we have to get 1, then 2, then 3. So we need that first one to be 0 factorial, right? N minus 1 factorial. So times n minus 1 factorial over, now I need 3 to these powers, 3 to the first, then 3 squared, then 3 cubed, so 3 to the n. That's it. Check it yourself. Let's let n be 1. If n is 1, what would you get? Positive 1. 1 over 1, 1, right? X minus 3 to the 1. What's 1 minus 1? 0 factorial is 1 over 3. So we get a positive 1/3 this to the first power. Positive 1/3 that to the first power. 2. What's negative 1 to the 2 plus 1? 2 plus 1 is 3. Negative 1 to the third, negative. So I'm going to get a negative 1 over, remember what this is in. 1 over 2 factorial, it's 1/2, right? X minus 3 to the second. What's 2 minus 1? 1. 1 factorial is 1 over 3 squared. So I had a 1/2, I had a 1 over 3 squared, and it was negative, and it was this squared. So negative 1 over 3 squared, 1/2 x minus 3 squared. This does it, okay? That's your challenge, okay? That's the thing that makes this difficult, is a lot of people can create the Taylor series off of the derivative and plugging in. Going from the Taylor series to the formula is the hard part, in my opinion. That's the big jump, the big leap. Now, we would want to clean it up. So can we clean this up? Natural log 3 plus some n equals 1 to infinity. How about this? Tell me what I'm doing. Negative 1 to the n plus 1. X minus 3 to the n over 3 to the n times n. What happened? Yes, well, but how? I took this factorial here and this factorial here, and I rewrote the bottom one as n times n minus 1 factorial, didn't I? So I can peel one off of this. When I peel one off, I get n times n minus 1 factorial, and then I cancel the n minus 1 factorial with the top and bottom. That leaves me with an n on the bottom. No more factorials. You could do ratio on this now. Yeah. I'm just saying you could. Yeah, this homework is going to be pretty intense. Trying to see if there's something else. Yeah, I mean, there's more we need to do here. On page 484 of your book, there's a table of common Maclaurin series on page 484. Unfortunately, I don't have the graphic to show you here. But anyone have their book with them? Oh, do you have it? Look on page 484, and you'll see they have a lot of the common ones written out already. So what I'd like to do now is I'd like to do this. I'd like for us to find the integral of sine x cubed dx. Who's got their TI-89? Who's all happy because they've got that? Do your TI-89. I want someone to find the antiderivative of that on their TI-89. Or your Nspire, if you got the Nspire, sorry. I keep that. You know, I'm not that up to date with things. Are you trying alpha? You have what? Oh, okay, you're looking it up. Okay. Anybody? Anyone? Anyone? Bueller? Does not compute? Did it just spit back the integral right back at you? That's the TI-89 does that when it can't integrate it. And Wolfram alpha is probably going to give you some weird error function that you never heard of before. This is another example of a function that you cannot integrate in closed form. Like there is no like this equals like sine something done. The only way to integrate this is term by term. So the first thing we need to do is expand this thing using Taylor series. So recall that sine x was equal to x minus, now this is what I did in the work here, right? So I did the work not in class, but I did it right here. So this is equal to this, x cubed minus 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. Now, if you look on page 484, it also has the series, the sigma notation, which is sum n equals 0 to infinity of, what is it, negative 1 to the n, x to the 2n plus 1 over n, 2n plus 1 factorial. Is that what it has in the book over there? Hmm? For sine? Yes? Okay? That is the Maclaurin series for sine because it's about a equals 0. So that's Maclaurin series. So if you have sine of something, this is how you can expand it. All right? We don't have sine of something. We have sine of x cubed. So I want you to look at this formula, the one I have in red, as like sine of u, and u, and u, and u, and u, and u here. So those are all like u's, right? So if I want to write out sine of x cubed now, I just basically replace all my u's with x cubes. So it becomes, what's the first thing here? I kind of got that in the way, didn't I? All my u's. You understand what I'm saying though, right? I'm just replacing all my x's with x cubes. So it becomes what? X cubed minus x cubed cubed over 3 factorial plus x cubed to the 5th over 5 factorial minus x cubed to the 7th over 7 factorial, which equals, so now come over here, and let's plug in x cubed into this formula. And what would you get for the sigma notation? Sum n equals 0 to infinity, negative 1 to the n, x cubed to the what? Yeah, 2n plus 1 all over 2n plus 1 factorial. What are we trying to do in this problem? What am I trying to do? Find the antiderivative, right? So now what I want to do is I want to find the antiderivative of this right here, right? The antiderivative of this, which means I want the antiderivative of this, don't I? Now there is a formula for this. Remember, the negative 1 to the n, the 2n plus 1 factorial, that's all my c sub n, isn't it? What I need over here is something that looks like x to a power. Right now it's x cubed to a power. So how can you get that x cubed out of there? How can I rewrite this? Equals, yeah, multiply it. So I get integral sum n equals 0 to infinity of negative 1 to the n, x to what power? 6n plus 3, good. All over 2n plus 1 factorial. Now technically there's a little dx out here next to this integral, right? You have to have like sine x cubed dx, and each one of these you're going to have a little dx. So the power here, right, and the x, that's one thing. The stuff in the blue here is my c sub n, right? So if this, let's just say this was x to the 10th power, what would the antiderivative of x to the 10th be? Antiderivative. 1 over 11 x to the 11th, right? And so what we're going to do is we're going to ignore this, right? And we're going to take the antiderivative of this. So what would the antiderivative of that yellow part be? So sum n equals 0 to infinity. I'm going to put the negative 1 to the n over the 2n plus 1 factorial. Haven't changed that. But then times 1 over what? 6n plus 4. That's just 6n plus 3 plus 1, right? It's just adding 1 to that power. If I add 1 to this power, I get 6n plus 4. And then x to the 6n plus 4. Now, we always have to throw out here plus a constant.
Does it book like solve the constant?
I don't think they do. You could, though, by trying, plug in 0 for x or something like that. All right. Can I check to see that this would work? Yes, let me check it. This was sine cubed, right? This was sine cubed, or sine x cubed. And we said this is it, expanded out, right? What would the first antiderivative be? What's the antiderivative of x cubed? 1/4 x to the 4th. So when I plug in 0 here, I should get 1/4 x to the 4th. Plug in 0, what do you get? What's negative 1 to the 0? 1. What's 2 times 0? 0 plus 1, that's 1 factorial. So this is all just a 1, right? Over here, plug in 0 for n. 1/4 x to the 4th. Okay, that's the first one. What should my next one be? That's really x to what power here? 9th. So that should be, when I take the antiderivative, it should be 1/10, right? 1/10 x to the 10th times 3 factorial. So now plug in 1. Oh, and it should be negative. 1 here, it's negative. 3 factorial. Good. I need a 3 factorial. What's 1 here? 1 over 6 times 1 is 6 plus 4 is 10. 1/10. Good. X to the 10th. Okay, that gave me my second piece. And then the third and the fourth and the fifth. So now, what do you think you would do? We're pretty much going to have to be done with class. But what do you think you would do if someone came in here and said, hey, look, integrate this from 0 to 1? From 0 to 1. Then you would do each of these, right? Like, what did we say that first one was? It was 1/4 x to the 4th, right? So you'd first do that from 0 to 1. So that would give you 1/4, wouldn't it? Then you'd do the next one from 0 to 1. Oh, well, minus 0. Like you plug in 1 first and you get 1/4. Then you plug in. Yeah, you'd subtract the next one, that integral, whatever it turned out to be. And then you add the next one and then subtract the next one. You keep doing that. And you can get, remember, this would be like the area under the curve between 0 and 1. This would be an approximation of that answer. The further out you go, the closer to the true area you would get. So if you want to get really, really precise, you go out, however many terms you want to get even better, go out further. And your computer can do this. See, the computer can do that. All right, well, your homework assignment, I believe, is on the last page of this. Let me tell you what problem you should probably skip because I didn't talk about it. Just a warning on number 9. A warning on number 9. It's the hyperbolic sine function. If you don't know what the derivative of hyperbolic sine is, go into your book into the section under hyperbolic functions, and it'll have the derivatives of sine hyperbolic in there. All right? It'll have the derivatives of sine of all the hyperbolic trig functions. It's probably on there too. Yeah. I don't know what page. What the what? I don't know what page it is. Yeah. Which one am I saying you should skip? Skip number 23 for right now.
Skip what?
Number 23. And you know what? You're probably not going to be able to do 31 or 43 yet either.
Keep going.
So that means of the assignment I gave you, 5 through 17 odd
8 problems.
and 29? What's 29? You can try 29, see if you can figure it out. Just remember on all these problems, you're supposed to find the radius of convergence. Good luck on your homework, everyone. Are we going where?